Hello and welcome to the second lecture of this short course entitled Behavioral Theory of Systems with a View Towards Data-Driven Control. In the last lecture, we argued that systems can be described set theoretically. Yeah, indeed, we said that a system is nothing but a curtailed version of all possibilities. How do we get this curtailed version? By providing laws that exclude various other possibilities, right? Indeed, we saw that the set of all possibilities is denoted by this big U called the universum, right? And the system is a subset of this all possibilities called the behavior of the system, right? That's how the behavior becomes a subset of the universum. We actually looked at various examples and tried to convince ourselves that this indeed is the most fundamental description of a system. What we lacked in the last lecture, however, is the essence of dynamics, right, which is absolutely essential for any kind of engineering study that we do, right? For example, what we mean by dynamics. In a nutshell, dynamics means that there is time involved in the system, right? What do we mean by that? Perhaps that is best understood through an example, right? Okay, so for example, once again, look at this electrical circuit, yeah, very well-known electrical circuit that you study in your first or second years of undergraduate studies, yeah. Okay. Right. So there is this voltage, there is this current. These are functions of time in general. For example, you often give this provide this circuit with a voltage source, right? It could be a sinusoidal voltage source, AC voltage source. It could be a battery which is being switched on at some time, right? Yeah, all sorts of such possibilities are there. What is meant by this is in fact the idea that this voltage actually is a function of time, and so is this current. Not just that, if you try to actually go ahead and solve this, go ahead and write down the equations for this system. Go ahead and write down the equations for this system and try to put in this extra, the so-called latent variables, right? They will also be functions of time, right? Okay. So what happens is that these variables, the so-called manifest variables or the latent variables, right? Both kinds of variables are now functions of time, and that is what is meant by a dynamical system, right? Both manifest and latent variables are now functions of time. Yeah, these variables are functions of time. So when these variables are functions of time, we call this system a dynamical system. Such dynamical systems can of course be be described as continuous time systems or discrete time systems. So how do we get the behavioral description of such dynamical systems? Yeah, as we will be able to appreciate very soon, the perhaps most general way of describing behaviors of dynamical systems, either continuous or discrete, is via this triplet. We have T, we have W, and we have this B, the behavior that we have already seen. This triplet is the one that will describe a dynamical system. Let me explain these three symbols. T will be called the indexing set. What do we mean by that? Indexing set in this case, in the case of continuous systems, can be the real line or the non-negative half of the real line, or for discrete systems it could be the set of integers or the set of natural numbers starting with 0. Likewise, W is the signal space. This is the set from where the variables are taking its values. Yeah? In our case, in most cases, it will be r to the power q. Yeah? The Euclidean vector space defined over real numbers. And of course, the behavior is the behavior of the system. Now, in this scenario, what do we, what is the meaning of this index set W and so on? In a moment's time, it will be clear what we mean by this T and W and the behavior. The indexing set. So, the dynamical system, the system's variables, right? Let me write a little bigger letter. The system's manifest variables, which are denoted by W, they will be functions from the indexing set to the signal space, right? Yeah. So, for a continuous time dynamical system, this W will be a mapping from R to, let's say, R to the power Q. What is meant by that? That means this W, this is the system's manifest variable, actually is a function of time. It takes it maps the time to its value, right? Remember this bridge circuit that I drew earlier? Let me redraw it quickly. Yeah, without these names. So, this is V. Now, V is a function of time. This is I is a function of time. So, the system's manifest variables are V and I, and they are actually functions of time. What it means is that this takes a time and maps it to a two-tuple Vt and It. So, indeed, the system's variable W is a function from the set of real numbers to the vector space of two tuples here, two tuples of real numbers here in this particular case, but in general it could be a q tuple, right? That is for a continuous time system. If you think of systems which are starting from t equal to 0, then instead of r you will have r plus, and when I write this bar, this means that it is a I am including the t equal to 0 point as well. Okay? Likewise, if it were a discrete system, then this function W will be a mapping from Z to r to the power q. In that case, it will indeed be a sequence, right. This is my time axis. It is a sequence defined on these discrete points. Yeah, and each point has a value associated to it. It's a sequence. Yeah, in general, it could be a q tuple. All these dots that I have written are elements from r to the power q. Right. So that's the description of a dynamical system. So obviously, in this case, then it would mean that the system's universum is in fact the collection of all possible functions from the indexing set to the signal space. Yeah, often the symbol that we use for this looks a little weird, but this is the symbol that we use. Yeah, this means the set of all possible functions of time, or the indexing set, all possible functions whose domain is the indexing set and its codomain is the signal space. Yeah, that's all the possibilities. That's the universum, and the behavior, of course, is a subset of that. Let us look at some concrete examples and convince ourselves what is meant by this kind of behaviors of dynamical systems. Yeah. So once again, let's go back to the bridge circuit that I drew. Yeah. So this is one terminal. Let me just take some time and draw it properly, because I would write some equations for it. Yeah, already I've made a mistake. Okay. Okay, this is one resistance. Yeah, this is okay. This is another resistance. Okay, so far so good. There is this. Let me make it a little easier. Let me get rid of this. Okay, this can also be there, no problem. I'm not going to solve these equations anyway. I'm just going to write the equations, so it's fine. Okay, I have the capacitance. Now I have the inductance. Okay, and of course these are the outlets. Yeah, this is I, which is a function of time. Let me not write this. The arguments is understood. This is V, and of course let me write down these numbers as well. R1, R2, R3, and C and L. Okay, and let me put down these latent variables as well. I1, I2. Let me say, okay, this is I3, and this is I4, and this is I5. Okay. Of course, likewise there will be the voltage drops V1, and I can put in some polarities following the direction of the current. Yeah. Right. So the equations that I can write down here will be, of course, okay, the Ohm's law kind of equations. Yeah. V1 equals I1 R1, V2 equals I2 R2, V3 equals I3 R3. Now for V4 I have to be a little careful. V4 is how much? Q equals CV, so 1 by C I4 integration from 0 to T I4 tau d tau. I hope I have not made a mistake anywhere. This is V4, and how is V5? V5 of course is L d dt of I5. Okay, These are the Ohm's law equations, and likewise we will also have the KCL KVL equations. What are the KCL equations? I equals I1 plus I2, and then that's at this node. Now at this node I will have I1 equals I4, I3 plus I4 in fact. I3 plus I4, and next if I apply KCL at this node, then we have I5 equals I2 plus I3, and then finally at this node if I apply again, I have I equals I4 plus I5. These are the KVL equations. Likewise, I will have the KVL equations. V equals V4 plus V1, then V also equals V5 plus V2, and then we have V3 plus V1 minus V2 equals 0, right? I move like this and this and this, okay? And I also have V5 plus V3 minus V4 equals 0, okay? And then I also have V5 plus V2 minus V1 minus V4 equals 0. I think that's it. I don't need any more. Yeah. So these are the equations that I have. All these equations together, I can call them, I can number them as like one set of equations and call them, let's say, star. All these equations, yeah, the Ohm's law equations, the KCL equations, the KVL equations, all of them I'm putting them under one umbrella and calling them the star equations. And then I can describe my behavior, the full behavior, as the collection of these functions of time V, I, V1, I1, V2, I2, V3, I3, V4, I4, V5, I5. Yeah, there's 12 variables which are actually functions of time. So this belongs to R5, sorry, R10, sorry, no, R12, sorry, my bad. R12 to the power R, that means I'm looking at all possible functions such that they satisfy these differential equations. Star is satisfied. All those integral differential algebraic equations are satisfied. That's my full behavior. Okay. This of course is a subset of the full universum, right? Now what is the behavior in this case? The behavior in this case will turn out to be all those Vi which is in fact a function from R to R2 because it's two tuple, such that there exists V1 I1, I am not going to write all of them, dot dot dot, up to V5 I5, yeah, this function which is going to be a mapping from R to R10 such that V comma I together with V1 I1, these latent variables V5 I5, this is an element of B full. That means if I can find these 10 tuple of time functions which together with this two tuple satisfy the star equations, then this Vi will be part of the behavior. right? So you see, what we have essentially achieved through this is that this behavior indeed, the way if you think about it for a while, it becomes obvious. This VI pair of functions are essentially those VI functions which satisfy the equations of this bridge circuit, yeah, which is given by this star, all the star equations. So the behavior in fact gives me all possible VI pair of functions that can occur in this system, right? So that way indeed this set of all possible solutions or all possible functions that defines the behavior of this circuit. So that's the system, so that's the dynamical system. Okay? Incidentally, these things, these functions which are functions of time, which are essential for describing a dynamical system, will be called trajectories. Yeah, I'm sure you have heard this term before. They will be called trajectories. Trajectories is plural, singular is trajectory. Okay? Now one might think that, okay, is it so that all dynamical systems are described by such equations? Well, not necessarily. For example, you already know a very famous case of a dynamical system, a celestial case of dynamical systems, which are actually not described by equations, but described by certain laws. Namely, the planetary motions described by Kepler's laws. Yeah, you remember we wrote Newton's laws, planetary motion equation using Newton's law of gravitation in the last lecture. Yeah, likewise, before Newton, in fact, there were these Kepler's laws invented by Kepler, which described the planetary motion. Indeed, it said that Sun is of course at the center, yeah, and then there is this planet. Oh, sorry, I should draw this planet much smaller than the Sun, right? Even this is a bit of an exaggeration, but okay, we can live with that. Okay, and what sort of trajectories or orbits are possible? Kepler says, Johannes Kepler says that, these orbits, not all, arbitrary orbits are not allowed. Only a very special type of orbits are allowed. What sort of orbits are allowed? Kepler's first law says that the first one says that it has to be an elliptic orbit, you see, with Sun located at one of the foci, with Sun at one of the foci. We all know that every ellipse has two foci. One of the foci would be the location of the Sun, right? And secondly, what is the speed of the planetary motion? Yeah, the speed of the planetary motion is such that if you draw this radius vector, then this radius vector sweeps equal areas in equal amount of time, right? Yeah, of course, it's not a constant angular speed, right? But the area that the radius vector sweeps, the area swept, that is the same per unit time. And thirdly, yeah, the period of this orbit, of this planetary motion, the period is directly proportional to the third power of the major axis of this ellipse, of the elliptical orbit. Newton's law's crowning achievement was to show that through Newton's laws of gravity, Newton was able to show that together this law of gravitation, of force, together with Newton's laws of motion, the dynamical equation, the differential equation that one obtains through those two laws, it shows that the solutions satisfy these three laws. Sorry, I made a slight mistake over there. It is the square of the period. Square of the period. Right? So, in other words, Kepler's laws is an alternative way of describing the dynamical system that is planetary motion. Indeed, if you think of Q as a function of time, right, that is the position of the planet, then this QT is the position of the planet at time t. So, assuming that the universe, discounting the current Big Bang theory, assuming that the system, the planetary motion, has been in existence from minus infinity, time minus infinity, it shows that Kepler's law says that this QT, this function QT, is a planetary motion. It describes a planetary motion if it satisfies, if and only if it satisfies the equations, the Kepler's laws. Right? And here is an example of a dynamical system where it's not given by equations, but it's given by certain laws. We can give several other examples of dynamical systems, but that's that will take more time, and that's not the point of these discussions. What we wanted to show is the basic rudiment of the description of a behavior when it comes to a dynamical system. Now, I will finish this lecture. I will end this lecture with two very interesting aspects of this kind of description of a dynamical system, namely two very important properties that we encounter all along in engineering studies about such dynamical systems can be very easily explained through the idea of behaviors, namely the question of linearity and the question of shift invariance or time invariance. Right? So, what is linearity? Okay, remember, behavior is a set, right? It is a subset of the universum, which for dynamical systems is W raised to the power t. B is linear if, by definition, W is a vector space. Please look up the definition of a vector space if you are not aware of it. And B is a subspace of this vector space. So, if W is assumed to be a vector space, then W raised to t automatically becomes a vector space where it induces the vector space property by defining it pointwise at every t, every element of t, of the indexing set. So, if B, the behavior is a subspace, then we call the system to be linear. And the moment it is subspace, you know, by the definition of subspaces, it satisfies the property of superposition, which is in fact used for defining linearity. But you see, there you need inputs and outputs and all sorts of added structures. Here you don't need that, right? Like for example, the planetary motion, it doesn't have an input and output, but still you can define whether it's linear or not. Okay? So that's the definition of linearity. Likewise, what is time invariance or shift invariance? One can define an operator sigma t, yeah, which is such that, you know, a sigma t is a mapping from this to itself. And how does it work? Well, if you take a w, then sigma t w acting on, you know, the value of this at t prime is by definition w at t prime plus t. That is the definition of shift. So, this is the backward shift by amount t, backward shift by the amount t. Now, it follows then obviously that if t is either z or r, then the system will be called shift invariant if sigma t of b is equal to b for all t in t. Yeah, for obvious reasons, if t is either r plus on the half line or natural numbers including 0. In that case, shift invariance requires that sigma t of b be just a subset of b for all t in t. You see, that is how shift invariance is defined so easily. So, we end this lecture with this description. In the next lecture, we will see that what can be said about behavioral equations. Yeah? We have already seen that the same behavior can be described by various systems of equations. Now, we ask the general question that when can we say for sure that two systems of equations will give rise to the same behavior? Yeah? This and many more is what we are going to discuss in the next and in the next few lectures. Okay? Till then, take care of yourselves. Bye.